Ladies and gentlemen, welcome to the first Global Engineering Symposium in Baku. The full-day event features a range of posters and oral presentations by 15 speakers and postgraduate students. In general, the symposium will consist of 5 panels. There will be 3 speakers in each panel, namely oil and gas engineering, chemistry, mechanical engineering, IT, and geoscience. Each panel will consist of 3 speeches, respectively 1 professor and 2 engineers. First, I want to invite here our project manager and also one of our speakers, Enver Mehmedli.
Welcome to our first Global Engineering Symposium. I'm glad to see you here. So here is as well the foreigner speakers. So I'm also thankful for them because they accept my invitation and they are in really great city in Baku. So everybody are asking why first Global Engineering Symposium? Because one of the aim is that, you know, in Azerbaijan, the networking is a little bit poor in engineering field. So I decided to organize with my team. By the way, I also grateful for my team. So we decided to organize this symposium. And yes, after 120 days, today it took place. So the aim is the making great network between Europe, between the world countries and in Azerbaijan. So, and I hope so you will get really great innovative ideas, and so enjoy your time. That's all. Thank you for your attention.
Now I am going to invite here Mrs. Mehin Jabrayilova to talk about Horizon Education Agency.
Hello everybody, welcome to our event. It's nice to see you in this day, in this event. I am a young economist and at the same time co-founder of Horizon Education Agency. Now I would like to give brief information about our agency and what we do and what's our aim. And Symposium is also one of our aims. And now I would like to speak about our services. And the day I understood that there is need positive alterations in the field of education in Azerbaijan, in my country. And I have distinctive projects about that. And I shared the idea with Anwar, and we started to run a social project about education and different fields of education. As you see, our aim is to get professional development, to help students, to help youth for their self-improvement, for their self-development, and for broaden their horizons. And mini MBA programs is one of them. Actually, we want to get open innovation in Azerbaijan. We want to be bridge between university and business and industrial fields. In this means we need help. Students need help. Business and companies need productive workers, and we can be bridge. We can prepare youth for them. It is one of our aims to get open innovation to help for formulation of entrepreneurial university in Azerbaijan. Additionally, we do some conferences, forums, tea talks, and other networking activities for sharing ideas, for their opinions, and to go further in their field. As you see from our services, the person can approach us, can say it's his or her aim and which field that he or she want to continue, and we can help them. We can find business, we can find internship opportunity, we can find university, we can find the exact area which is suitable for them. And additionally, I applied with this project to Social Entrepreneurship for Youth program and Global Entrepreneurship program, and this idea was winning, and for the months we tried to work on it and making something productive for youth. And if you have any other questions about our goods and services, you may approach me. I'm here, and additionally via social media you may write me. And I'm really thankful you for listening, for your coming here for this day, and enjoy your day. Thank you.
Mrs. Günay İlhamlı, a representative, one of our sponsors, Azercell LLC, will speak.
Dear ladies and gentlemen, my name is Günay İlhamlı. We are so glad to see you in Azerbaijan. In our country, there are many kinds of fruits and vegetables, and we, as Azercell LLC, have been engaged in production and export of hazelnut kernel for more than 20 years. The Azercell Manufacturing and Trading Company is one of the largest national hazelnut processors and exporters, led by Azercell founder İlham İsayev. This small shop has grown over several decades into a large company with the impressive export volume of more than 4,000 tons of finished products per year. As of today, the company's delivery capabilities have expanded to include the CIS and most European countries. We have achieved high performance rating in the field. Some certificates can confirm the high quality of specific products. Our company is better described by these starting figures: 12 years of international market experience, 20 years of hazelnut large-scale production, up to 12 tons of shelled nuts per day. 120 hectares of the company hazelnuts grow in Zakatala. A team of 84 qualified processing, harvesting and exporting specialists, and an annual sales volume exceeding $22 million in 2018. Today we produce and export up to 25% of the total volume of Azerbaijan hazelnuts, and our market share is growing annually. Thank you for attention.
Thank you very much. And I'm going to invite Mrs. Dinar Mehmedova. She will talk about one of our other sponsors, SOCAR LLC.
Good morning, everyone. Glad to see you over here. Welcome to Symposium, this international symposium. Separate special thank you to our foreign professors and participants who thankfully accepted our invitation, and they're here to share their experience, to share their knowledge. I'm not going to talk about METAC, advertise METAC, what we are doing, what we are, and etc. So METAC is talking about itself. So I'm going to talk about your career. So if you are here, my understanding, you are ambitious, you are enthusiastic person, and you are ready to start your career. But before starting your career, first of all, you have to think, are you ready for a dynamic career? What are you doing for that? What you need to do in order to achieve your target? And what are your targets, life targets, career targets? So, my understanding, first of all, I have more than 20 years experience, professional experience, and I would like to give some tips to you how to do professional career, how to be well known in the industry, well known in the sphere what you are doing. So here's some brief information about METAC, but I want your focus on your career perspective. Career perspective in the industry, in professional industry. First of all, you think where you are now, in which area of industry you want to continue your career, in how you would like to continue. You would like to continue in industry, in operations industry, which is very essential for you. Believe me, operation experience, production experience that you will get now is the best that you can get in your life. And METAC is giving this opportunity not only for professionals, for young generation as well. So you can try yourself in METAC as well. So we are doing metal, we are doing plastic, we are doing agriculture as well. So you can try yourself in each of these industries. So we have several, for example, just give you a brief example. So we have our branches, we have our divisions in Baku, which is, by the way, very close to this hotel, to this location. We have in Neftchala, we have in Balakhane, we have in Gusar, huge agriculture areas over there. And we have in Sumgait, everywhere we have metal production, plastic production plants. Think about your career, think what you want at the end, and we as METAC will be happy to see each of you, to share your experience, and we are ready to help you to build your career on professional level. So we are doing history of metal and plastic in Azerbaijan. I would like to invite you to make this history together. Come and join us. Thank you.
Now, I want to invite here Mr. Rashad Azizov. He is a representative from the High Technology Ministry of Azerbaijan.
Thank you very much for introduction. First of all, I hope that this symposium will be very successful, because the science is the very important part of the innovation policy that is held in our country. As you know, last year was established the new innovation agency under the Ministry of their Transportation, Communication and High Technologies, and I'm the representative of this state body, and we are very glad to support this symposium. You are very young, but you are the future of our country, and we hope that your innovative ideas will bring the success for yourself and for the companies that you will represent, and of course for the whole our country. During our education process, we are planning our future. And if you fail to plan, then you plan to fail. We must do vice versa. That's why go on in your education process. Please pay attention to your scientific ideas, because your scientific ideas is the key to our future success. Thank you very much for your attention, and my expectation from this meeting, from this symposium is very great, because I hope that it will bring the new young people's new ideas that can be used in their future science of our country, and also in the different projects that are held by different state bodies. Their themes of these symposiums is very various. It's not only in transport or communication, it's for energetic, oil industry, others, chemistry. We must understand that innovation and success can come from any field that you represent. And I hope that our joint efforts, the efforts of the state, of the private sector, and also from you, the science, will come and bring us to the success. Thank you very much.
Thank you very much for listening and for presentation. Now, I'm going to invite here the Deputy of Azerbaijan Parliament, Mr. Hüseyinov.
Hörmətli tədbir iştirakçıları və mən bütövlükdə tədbirin həm məqsədini, məramını çox ürəkdən alqışlayıram. Və doğrudan da tədbirin bu şəkildə təşkil olunması və bugün dünyanın özünün marağında olan bir temanın seçilməsi, bir mövzunun seçilməsi və bu mövzu ətrafında, bu məqsəd ətrafında fikir mübadiləsi aparmanız məni çox sevindirdi.
Dears, I really appreciate the event that it organized and you come together. It's one of the hottest topic in the world to speak about this, to be here. It's really pleasure.
Və bugün dünyada 4-cü sənaye inqilabı artıq gedir. Və Davos İqtisadi Forumda da 2019-cu ilin əvvəlində Davosda, bilirsiniz ki, Davosda dünyanın beyin mərkəzidir və dünyada gedən qlobal iqtisadi proseslər və bütövlükdə iqtisadiyyatda, siyasətdə və ekologiyada və bütövlükdə gedən proseslər, qlobal proseslər Davos İqtisadi Forumunda təhlil olunur, proqnozlaşdırır və siz də xatırlayırsınızsa bu iqtisadi forumda ən başlıca mövzu dünyanın 4-cü deməli sənaye inqilabı ilə bağlı idi. Və bugün də siz, ona görə mən çıxışımın əvvəlində alqışladım ki, siz də bugün istiqamətiniz və bugün apardığınız müzakirələr bax bu ətrafdadır.
It's the area of industry, international, all world countries doing. They discuss this topic, and therefore today we will speak about this topic. It's also the beneficial.
Və ümumilikdə götürdükdə təhsil məqsədli olmalıdır. Təhsil hər hansı bir ali təhsili, ali məktəbi və yaxud da deyək ki, universiteti bitirmək yox, o universitetə, o təhsili seçərkən hansı peşənin sahibi olacam, hansı yerdə özümü görəcəm. Bax, elə siz birinci növbədə o universitetlərə üz tutarkən onun nəticəsini bərbaşdan görməlisiniz. Və mən də görürəm ki, artıq o nəticənin görülməsi yox, onun bir də əldə olunması ilə bağlı siz artıq qəti fikir qərarlaşdırırsınız, məqsəd ortaya qoyursunuz və bugün seçim aparırsınız və o təhsilinizi harada tətbiq edəcəksinizsə, onun üzərində fikir mübadilələr aparırsınız. Bunun özü isə bir daha onu göstərir ki, doğrudan da gənclər məqsəd yönlüdür. Gənclər bugün cəmiyyətdə və ümumiyyətlə gələcək həyatda özlərini harada görürsə, bax bu gənclərin bir daha dəyəridir, bir daha bütövlükdə bu zalda iştirak edən, eyni zamanda bu tədbirdə iştirak edən bizim mütəxəssislərin və xaricdən gələn bizim belə deyək ki, tədbirdə iştirak edib mütəxəssis qismində öz tövsiyələrini verənlərin də mən o fəaliyyətini çox yüksək qiymətləndirirəm və bütövlükdə tədbirinizə uğurlar arzulayıram. Gəncliyin bu tərzdə belə bir araya gəlməsi əlbəttə bir millət vəkili olaraq məni sevindirir. Çünki ölkənin gəncliyi bax belə müasir düşüncəli, gənclərin çiynində olacaqdır, yaxşı mənada. Sizləri bir daha belə deyim, ürəkdən alqışlayıram, uğurlar arzulayıram.
I will translate. Yes, I'm really hopeful about future of our country, that young generation, they do some useful activities like this. As you know, education starts from beginning, and I'm really hopeful that you are here and you are in the second stage. You want to do something to form network for yourself. You have just specific aim and you are goal oriented. It's really nice to me to see in this audience as a deputy, as a politician. Thank you.
At the moment, I'm going to introduce our speakers to you. Dr. George Barakos, Mr. Jabrayil Eyvazov, Mrs. Emma Kocik, Dr. Elshan Abdullayev, Professor Plumper Felix, Dr. Ashish Set, Mr. Elvin Rustamli, Dr. Sharul Dol, Mr. Shamil Islamov, and Mr. Elmir Abbasoglu, Mr. Ulvi Fatullayev, and Mr. Siraj Hasanov, and other one professor, Professor Pınar Mengüç, Professor Dr. Tulparkhan Salavatov, and Mr. Enver Mehmedli, you know him. Thank you for very much for your attention, and now I'm going to invite here our first panel speakers, Professor Tulparkhan Salavatov, Mr. Jabrayil Eyvazov, and Mr. Shamil Islamov.
I'd like, our department was founded on the initiative of academician Leonid Samuilovich Leibinzon, who came to Baku from St. Petersburg after great October Socialist Revolution as a refugee, you understand. And this person continued his activity in our Azerbaijan Oil and Chemistry Institute, that period, named that. And he was teacher and mentor, my teacher, academician Azad Khalilovich Mirzajanzadeh. Recently, we celebrated his 90th jubilee, but unfortunately, he died. The ideas developed and proposed by Azad Khalilovich are the scientific heritage and the direction followed by staff on the department in this day. Academic Mirzajanzadeh, one of the founder of fundamental science in the field of mechanics, technology, development of oil and gas fields. Academician of the Academy of Science of Azerbaijan Republic, Republic of Bashkortostan, honorary oil industry worker and honorary worker on the gas industry, twice State Prize of Azerbaijan, honorary scientist and technician of the Azerbaijan Republic. It can be noted that distinctive future of the academician school of academic Mirza Canzadeh is that phenomenological theory and the proposed approach to filtering viscoplastic and viscoelastic system are used in solving numerous problems of extraction and transportation of non-Newton system. Research and discoveries related to drilling, oil and gas production, and the use of completely new material in special equipment. In general, it can be stated that the name of academician Mirza Canzadeh is associated with the abandonment of the traditional approach in the development of oil field and is abandonment of the laws of linear filtration. For the first time in the world practice, his scientific school suggested that oil and gas production facilities should be considered as self-organizing dynamic systems that are not linear and stable and non-stationary. When training the scientific school, the academician attach great importance to the transfer of modern knowledge from the teacher to students. To implement this process, which rigorous hard work, Mirza Canzadeh attached great importance to the organization of regular scientific conference, seminars, and school seminars. As a result, the influence of the scientific school overstepped the border of Azerbaijan and the former USSR, and it was recognized worldwide. Mirza Canzadeh had one slogan: do not be stingy to give ideas. He believed that in each area, a specialist can be considered only as a person who is not a specialist, who can convey the essence of his specialist in simple language without resorting to formulas and graphs. Academicians often used figurative comparisons in oil and gas production. So for example, very interesting example, he said us, well, as a capricious woman, this is word academician, approaching the well, the engineer should be in white wool gloves, and this approach should be gentle. Otherwise, a capricious woman can take tevenji. He also called his student to be able to listen to working well, production well. Since noise chaos is many cases is a carrier of information. Before explaining any complex topic, our teacher, linguistic methods revelated the philosophy of this process. The approaches considered by him gave development to the whole Azad Malim school, and the result, this school being international, stepped over all geographic boundaries. The scientific center of the school, I mean scientific school Mirza Canzadeh, were Baku, Moscow, Ufa, Ukhta, and St. Petersburg. Azad Mirza Canzadeh prepared highly qualified scientific personnel for the interspace of the USSR and for many foreign countries. Currently, his personal work in Bashkiria, Moscow, Tatarstan, Komi, Uzbekistan, Turkmenistan, Ukraine, Egypt, Iraq, Syria, Algeria, Bulgaria, Poland, Yemen, and other regions. The use of mathematical studies in oil and gas production was first proposed by Azat Mirzajanzadeh, and many works were performed in this area. In the monograph of, very interesting monograph of academician Polubarino Kochina, great synthesis, dedicated to the 15th anniversary of Soviet mechanics, there is a section devoted of Mirzajanzadeh and the generalized Darcy law proposed by him, which was called the Mirzajanzadeh formula. In this formula, as an additional element to the Darcy filtration law, he took into account the initial pressure gradient. The result obtained by Azat Mirzajanzadeh is fully considered with the approach, aphorism, very interesting, wonders in the small. Here we are talking about those small ones which consolidating result in compensated. And we must overcome these small ones. This outstanding result obtained by academic Mirzajanzadeh made it possible to make a fresh look at the process of development and the exploitation of field. The extracted oils of which show animals' properties. As a result, the result obtained by academician Mirzajanzadeh gave impulse to the creation of new methods and ways of developing such field, and as a result, ensured the future development of oil field mechanism and underground hydraulics. Mirzajanzadeh executed a number of original works on problem in gas condensate field. He established an important fact of the presence of limiting pressure gradient and created a theory of the development of gas and gas condensate field. Under his leadership, developed a method for determining the sorption capacity of rocks based on data from non-stationary filtration of gases in porous medium. Academician Mirzajanzadeh conducted his research and teaching activity from 1959 to the end of his days at the Azerbaijan Institute of Oil and Chemistry. Later renamed the Azerbaijan State Oil Academy, and here he created the center of his scientific school. In this training center, he began his work as a head of the theoretical mechanics department, later headed the department development and exploitation of oil and gas fields. Along with this, as a result on the recognition of work towards the center space in the USSR, he was invited to cooperate in many research institutes and universities. The personal contribution of Azat Mirzajanzadeh to the school be created was the preparation of very fantastic number, more than 400 candidates of science and more than 100 doctor of science. In the training of scientific personnel, Azat Mirzajanzadeh had his own method, which consisted in the fact that candidates for postgraduate and doctoral studies were selected by him. He himself defined topics for him, and the setting tasks and solving them were controlled by him without reassigning to any else. Explaining to postgraduate studies and doctoral studies, he never said, "Did you understand?" But he said, "Could I say?" It is a little bit strange, but why he said that? Responsibility for understanding take to himself. Study load, Azad Muallim, was very large. He thought can be said at all faculties, our university. At the same time, his goals was identify the most capable students in order to successfully involve them in scientific works. For a long time, under leadership of our academician, was Congress Factor 4. That is reducing in the new technological operation the amount of the used chemical reagent, double the efficiency of the process twice. At this conference, very interesting technologies were discussed, which later found applied in the field.
Now, our second speaker of first panel, Mr. Shamil Islamov.
So convenient for me. Okay. Hello, everyone. I'm Shamil Islamov from St. Petersburg. I'm currently Reservoir Engineer at company BP part-time, and currently I have a PhD program at St. Petersburg Mining University at the development and exploitation of oil and gas fields. Today, it's a great honor to be here. Thank you for invitation. Today, I want to present the topic about substantiation for well killing technology for fractured carbonate reservoirs. Okay, about the relevance. The process of well killing technology in one of the well from Russia oil and gas condensate field in Volga-Ural province, complicated with several conditions such as fractured carbonate reservoirs, high gas oil ratio, a lot of wells after acid treatment, after acid fracturing, and so on. We analyzed the efficiency of well killing technology for the last 2 years, and you show only more than half a person is successful. It is a very not good indicators, and on this way we the main purpose and the main aim of this work is increasing the efficiency of well killing in the following abnormal conditions, abnormally low formation, abnormally low formation pressure, high gas factor, high gas oil ratio, and wells after with fracture. To do this one, we analyze a lot of kind materials, a lot of scientific papers, and there are two ways to decide this problem. It is increasing the blocking fluids viscosity for well killing and blocking and a fracture using solid systems. Okay, this slide shows a lot of systems such as water systems, hydrocarbon and blocking system, and only blocking systems show the positive results. Only blocking systems used in the abnormal conditions such as height, temperature in the formation, in the bottom hole formation zone, abnormal low formation zone, abnormal height, formation pressure, and so on. And to develop this, the new blocking hydrophobic emulsion composition with solid system, we used only high precision equipment from our department, such as densimeter, viscosimeter, coral flooding test equipment, and so on. The first tests include physical and chemical tests, and then rheological tests, and then determination of blocking properties by using filter press, and finally we modeled reservoir conditions by using core flooding equipment. Okay, about physical and chemical studies. Later, I want to say why we select this composition and why and the type of solid system. Okay, this composition is very simple to use. Include only 3 components such as oil or kerosene, emulsifier, and aqueous solution of chloride calcium or natrium. And next one, this composition is thermostability and sedimentation stability, and corrosion activity is not exceed the established norms. Okay, by using filter press, we select optimal concentration of solid system, microcalcite, and where we modeled fractures different by different size from 1.1 millimeters to 5 millimeters. We modeled and modernized this equipment. And then I suggest to look this test, how we do this test. We used chalk, shell rock, filler, and the other kind materials from service companies from Schlumberger, Halliburton, and Baker Hughes. And as you know, a lot of materials, yes, not only emulsion, for example, polymer systems, as like water soluble polymer gel. We only one material shows the positive result. It is a microcalcite. This material successfully blocked the fracture. This is the results of tests, and after that we create by using core flooding equipment from company core test systems, create reservoir conditions and test this composition before using the in real oil and gas fields. Okay, previously I said about the composition. Yes, this composition is very simple to preparation to use in oil and gas on the field. And in additionally, we use only technological reservoir. The technologies of well killing is blocking the preparation zones up to the 100 meters up, and we tested this composition in real to oil and gas in two oil wells. This field belongs to Gazprom Neft oil company, and we got positive results. And you can, on this slide, you can see the cost of the well killing technology by using basic methods and new methods. And I want to say this composition is 2 times cheaper than previously used. On this slide you can see the main conclusions. Yes, this is all what I want to show you. This topic is very important from Russian Federation, because we have a lot of reserves, carbonate reserves from Russia, as like Azerbaijan, yes. And this is all. If you have a question, I can tell you.
Thank you very much for your presentation. Now, Jabrayil Eyvazov. Mr. Jabrayil Eyvazov presents us his presentation.
Thank you very much. Hello everybody, welcome to the first Global Engineering Symposium. My name is Jabrayil Eyvazov. I am Senior Reservoir Engineer at State Oil Company of Azerbaijan Republic and also a PhD student. Today I am going to talk about PVT tests, why PVT tests are very important in oil and gas industry, what are purposes of using PVT tests in oil and gas industry. As you know, there is a huge number of reservoir fluids which we withdraw from the reservoir, but in oil and gas field it is difficult to do deeply investigation of these reservoir fluids. Therefore, we need deeply analysis of reservoir fluids which we take from the reservoirs. And except that PVT analysis is very important in reservoir management. I will talk a little bit about this in other slides. And except that PVT analysis is very important measurement of solids formation and other non-hydrocarbon fluids and so on. And effects of PVT tests in oil and gas industry. Firstly, it affects the design of production facilities. What we understand when we say design of production facilities, for example, we define the range of condensate gas or oil from PVT analysis. We define dew point and bubble point pressures, and except that we now mixture of reservoir fluids, and therefore based on this information we set up separators. It can be for one stage separator or 2 stage and several stage separators. And compatibility with pipeline transport. For example, we can need, based on PVT analysis, we can need high pressure gas pipeline or low pressure gas pipeline. We can, for example, only for gas exporting, we can need 2 pipelines. Product sales values, refining maintenance cost, and reservoir assets in general. It is a simple illustration of gas chromatography. Based on this tool, we define component composition of the reservoir fluids. Here we inject our reservoir fluids, and there is two types of columns, packet or capillary columns, and packet columns mainly 1.5 meter in length. And here detector, there is two type detector in PVT tests, frame identification detectors, and second one, thermal conductivity detectors. Mainly for reservoir fluids, we use thermal conductivity detectors. Here define, for example, percentage of methane, ethane, propane, and so on, benzol, and other components. We can divide PVT tests into three parts. First one is primary test, which we can do in oil and gas fields. It is simple test and routine test. By using this test, we can define specific gravity and gas oil ratio based on fluid sample. And second one, which we are using in reservoir engineering, this is main types of PVT tests which we are using in reservoir engineering: compositional analysis of the system, constant composition expansion, differential libration experiment, separator test, and constant volume depletion. For example, constant composition expansion, almost in all fields we do this PVT analysis test. And differential libration tests we do only for oil reservoirs, and constant volume depletion we do for condensate reservoir. And separator test mainly is very important for oil reservoirs because we should do differential libration experiment and separator test together. We need this separator test for adjustment oil formation volume factor and gas oil ratio. And another type, specific type of PVT test is slim tube tests and spelling tests, and both of them we use to define minimum miscibility pressure and minimum miscibility concentration. First one, we will define minimum miscibility pressure and minimum miscibility concentration. And constant composition expansion. Main target of using constant composition expansion test to define saturation pressure or dew point pressure. Saturation pressure, when we use constant composition expansion test for oil reservoirs, for gas condensate reservoirs, we need to define dew point pressure. Is a thermal compressibility coefficient, compressibility factor of the gas phase, and total hydrocarbon volume as a function of pressure. It is a basic illustration of constant composition expansion test. We take reservoir fluid sample from the reservoir, and we set PVT cell, and we put this reservoir fluid volume into the cell, and we set reservoir temperature. For example, it is 100 Celsius, and we set initial reservoir pressure. And here, mainly in gas condensate constant composition expansion test, we have mercury, and then in next stages we become to reduce pressure, and here first I'd say condensate trace will become to appear, and it means that it is dew point, and when we reduce our pressure, condensate will become to generate. And differential libration experiment, as I said, it is for all reservoirs, and for reservoirs here also we set we take reservoir fluid volume, and put in the PVT cell, and we set reservoir temperature and initial reservoir pressure, and we reduce pressure, and we take gas from the solution, and as you see here, pressure will become to reduce, and in last stage it is remaining oil. And by using this experiment, we can define gas specific gravity, gas formation, oil formation volume factor as a function of pressure, oil density, oil viscosity, and so on. And another test, constant volume depletion test, is we did this test only for gas condensate reservoirs. It is also similar illustration with differential aberration test, but we use only gas condensate reservoirs. But here the main differences is initial temperature is the dew point pressure. I should mention that we use constant volume depletion experiment with constant composition expansion tests. We cannot do only one this test for gas condensate reservoir. By using constant CC test, constant composition expansion test, we defined dew point, and we start our experiment with dew point pressure, and then we reduce pressure, and you see that after reduction of pressure, gas we expand, and we remove gas, and we define gas formation volume factor, liquid dropout, relative volume, gas viscosity for all pressure steps. Separator tests. It is also very important test in oil gas industry. Why we do this separator test? Main idea is to define volumetric behavior of reservoir fluids in different separator stages and stock tank oil. We should find optimum point, optimum pressure, temperature, and operation properties to get more oil in stock tank. And it is also basic illustration of a separator test. And when we extract reservoir fluids, and here first stage, and here we take gas. It goes stock tank for gas, and here in next stage remaining oil goes in the next stage, and here also some parts of gas will be expand, and we will remove this gas, and here we find only oil, and here we can find stage gas oil ratio for here, and total gas oil ratio by using these equations. It is a real project in Azerbaijan. This project was done in Tempest software, and it is CVD test. It is offshore field. This sample taken from offshore field, and as you see, our experiment starts from dew point pressure, which we find from constant composition expansion test, and we find liquid dropout as a fraction, or it can be as percent, produced moles, and gas Z factor for all stages. And it is adaptation or matching of liquid dropout. These dots illustrates real data, and this is which we adapted by changing some properties in related liquid dropout. And it is for produced moles, gas Z factor. DLE test for well number 3. It is also field in offshore, and it is bubble point pressure, and it is oil formation volume factors. For this pressure, we defined gas-oil ratio. This means that after bubble point, as you know, first gas bubbles will be expand, and it is gas-oil ratio for this pressure and oil density. It is adaptation oil formation volume factor. In gas condensate reservoirs, adaptation of liquid dropout very important because it defines gas condensate initially in place, condensate volume, and adaptation of oil formation volume factor. It's very important to find original oil in place, correct original oil in place. It is gas oil ratio. And it is another DLE test for another wells. And separator test. Why separator test very important? As you see here, it is this temperature, in this pressure values, all densities and values, and second stage separators and stock tank. Why we need separator tests? Therefore, because we need to adjust oil formation volume factor and gas-oil ratio, which we get from differential liberation expansion tests. Because it is which we get from this DLE test, it is not correct one. By using these values, we cannot correctly define oil flows and original oil in place. Therefore, we need to adjust these parameters. By using these steps, we calculate several parameters. It is, how to say, theoretical background of this adjustment. By using these softwares, how to say, software will do for us this adaptation. For example, it is a simple illustration. For example, we get solution gas-oil ratio from DLE test, and by adjustment of by using separator adjustment gas-oil ratio, we got that gas-oil ratio should be lesser, and it is for it is for oil formation volume factor. As you see, oil formation volume factor which we get real one is less than from DLE test, but there is one factor that if our oil formation volume factor is less than DLE test, it means that by adjustment of separator test, our original oil in place will be higher than if we will use DLE test. Okay. Thank you very much.
I'm going to invite here our second panel speakers, namely chemistry, and Mr. Professor Felix Plamper from Germany, and Mr. Elvin Rüstemli, Mr. Elmir Abbasoğlu.
Okay, thank you very much for the introduction, and I also thank the organizers for giving me the opportunity to share something about my research here in this wonderful city of Baku. I really appreciate that. Actually, it's a bit hard to condense my research within 15-20 minutes. I try to do so, so I want to talk today about non-equilibrium polymer systems. So polymers are long molecules, chain molecules. They can be water-soluble, they can be non-soluble in water, and you can even combine different chains into one molecule, and then you have chains or molecules which are partly water-soluble, partly non-soluble. So the insoluble part wants to get rid of water contacts, and that happens by assembling a number of these molecules into these micellar entities. And these micellar entities can have different structures. As you see here, spherical micelle, worm-like micelle, a vesicle, or even aggregates of vesicles. So this is one part I want to talk about today, and the other one is about electrochemistry. So the idea is just to use a switch on at the wall and to induce changes in properties of your system, polymer system. So these two things I want to talk today. So after addressing in a short non-equilibrium system in general, I want to talk about an electrochemical solubility switch, and then how we can use micelles in a non-equilibrium state to change the properties upon request. So let's start here with this schematic energy landscape, which is taken out from a review from Hermans, and it tells us if you are in the global minimum of this energy landscape, that's the most stable configuration, the most stable structure in your system. So here you are in equilibrium, but apart from that, you can have side valleys where you are maybe entrapped and you cannot get out easily. For example, in this case, you need to overcome a high barrier, and that's not easily possible unless you melt down your peaks, and then you can have this state where you, by just using small deviations from metastability, the whole system will run towards the equilibrium state. And at the same time, major property changes will occur. Now, I'm interested in these red dots here, but recently this dot was addressed in literature very much. It's about the dissipative non-equilibrium self-assembly. That means you need to provide fuel, you need to push in energy all the time in order to keep that state, and once the fuel is out, then the whole system runs towards equilibrium. Now, the editors of these reviews, they state that chemistry has for most of its time focused on the synthesis of systems that are stable. This makes sense, as stable molecules and materials are easy to make, store, transport, sell, and utilize. Further, non-equilibrium states and associated kinetic processes have, of course, also received attention, but usually only as transient regime in the synthesis and preparation towards the final equilibrium state. So this is the state of the art, but it tells us there's more to come. So we want to address that, and I start with a very simple example. It's a very poor man's mind depiction here, what may happen to, for example, now we don't have classes here, but what happens to a glass or glass window on long time scales. So glass is a non-equilibrium state of material, and it also tends to minimize the potential energy. This one aspect of the non-equilibrium state of glass, it wants to minimize its potential energy, wants to flatten out. And I take this this example actually from some observation in cathedral windows where the bottom of the windows are thicker than in the top. So people argued, okay, this might be glass flow on long time scales, so hundreds of years, the glass might flow. But actually, if you take a look into the physics, that won't happen in 500 years. That happens maybe in millions of years. So that's not the real reason. But there's another example which nicely demonstrates what can happen on different time scales. So this is a so-called pitch drop experiment. Some people call it the most boring experiment ever, because nothing happens except every 10th year, one drop of pitch of this black stuff here drops down. And otherwise, nothing happens. However, if you use short time scales and you have impact, the whole thing will splinter apart in thousands of pieces, so it's very brittle. So you have here different properties united in one system, and the idea is that we change between these time scales in a way, and we want to freeze a certain structure and a certain time scale by using plasticizers. But however, if we take the plasticizers away, we get the brittle state, and if we add plasticizers, we get the fluid state, which then can adapt to the equilibrium state easily. But once we freeze the system, we can bring the system to another conditions where it's not in equilibrium state, and then upon triggering, it will run towards the equilibrium. Now, I will explain that later in more detail, but here in this picture there's also a battery, because that brings me to my next point, because we can use also electrochemistry to bring a system out of equilibrium. So if you all know that battery is a non-equilibrium system. So once you shortcut it, you will see that there's energy stored. So at the same time, you can charge a battery, you can bring your system out of equilibrium again. And so the system is only in equilibrium when the potential difference between the poles is zero. So once you have a potential difference, the whole system is a non-equilibrium state. So people use that, for example, for polymer systems, so-called redox flow batteries. It's just one example where they used polymers which can be oxidized, and then on the other side polymers which can be reduced, and they put them on both sides of an electrochemical cell, and it's separated simply by a very easy or very simple dialysis membrane. So these two polymers want to react once they are charged. They want to react, but they cannot, because here it's the dialysis membrane. They cannot meet. And the only way to react is then that you shuttle electrons here via the LEDs, and you have then battery again. And once it's discharged, you can charge it up again. So this is one example how you can achieve a non-equilibrium state. And at the same time, we also adapt this principle for our system. So shortly, we use electrochemical stimulation for non-equilibrium properties, and then we use triggerable glass transition temperatures, so shifting the fluidity of the material by some means, and a pathway-dependent preparation strategy in order to achieve really non-equilibrium micellar structures. And this is done by using orthogonal triggers on glass transition and structure change. How do we arrange the structure change? We imply so-called thermoresponsive polymers, which change their solubility with temperature, and then you can also have a structure change when you change the solubility, and then you can freeze in your system by taking away the plasticizer, and upon request, you can again make it more mobile, and the whole system will run towards equilibrium. Now let's start with the first part of the electrochemical solubility switch. So this is an older example where we used these star-shaped polymers with a cationic moiety, and we used here this polymer together with oppositely charged counterions, and these so-called ferricyanides, they interact strongly with this blue cationic moiety and makes it insoluble. However, the ferrocyanides, they don't interact strongly with the blue entity here, and it's still soluble. So by using electrochemistry, you can change the ratio of these two entities, and at the same time change also the solubility of the blue part. And if it's insoluble, you get vesicles in a very simple 2/2 cell setup. And indeed, we get these vesicular structures when we oxidize. So in this state, when we reduce, we go back to the unimolecular dissolved polymer. Now, this is a peculiar example because you change solubility at electrodes. And typically what you get is that you form films, film formation, and you have electrodeposition at electrodes. So we wanted to know more about this system, and we did that by using a so-called rotating disc electrode. So this is the yellow part is the electrode, and it's embedded in an insulated cylinder, and the cylinder rotates. So there's liquid close to this electrode, and it feels also the centrifugal force of the electrode and is swept away. So that means new liquid needs to approach the electrode. So you have a very defined streaming profile close to the electrode here. Now, it's an electrode. You can scan the potential. So with time, you can increase the potential. And unlike in cyclic voltammetry, where you get a maximum in the current potential curve due to depletion of your interface with electroactive species, you get here a plateau, a limiting current, which is due to the fact that you have a constant transport of electroactive material to the electrode. Now you can change your system and put also a ring electrode around the disc here, and then the products of the disc reaction need to sweep along the ring. So you detect the products here at the ring when you keep the constant potential and scan the potential at the disk, but the current's a little bit lower, and so this is given by the so-called collection efficiency, that you do not detect 100% of the products which have developed at the disk. Now, let's take a textbook example. So this is just ferrocyanide. You start here, you do a scan, you oxidize it, you get current, you produce ferrocyanide, and then you scan back, and the two curves are superimposing very well. Same true for the ring current. Now you add this polyelectrolyte again, so in a certain ratio, and then you start again scanning, nothing really happens, looks rather the same, but once you scan back, you see suddenly that there is a pronounced cathodic peak, this peak. And this peak tells us that the product of the forward reaction has been stored at the electrode and can be reduced now upon backward scanning. And if you take out the electrode, this is a platinum electrode, then you see that upon stopping here, there's a yellowish deposit of the ferrocyanide and the polymer complex. And if you reduce it again, you get a pure platinum electrode back because it's dissolved again. So we can now use these peaks to learn something about the deposition efficiency. So how efficient is our current or our charge which we transfer over the electrode to deposit the material at the electrode. So without going into detail, I would just mention some examples. So this is the textbook example, no deposition, of course. Now we take the monomer, not the polymer, but just the monomer, no deposition. Deposition efficiency is 0. We take now a rather short linear polymer, polyelectrolyte. Then we see pronounced deposition. Now we extend the chain even further, then the deposition efficiency is lowered. It's smaller, it's decreased. Now we increase branching, it's even further decreased. And now you can, the reason for that is that you have more likelihood for intramolecular cross-linking than intermolecular cross-linking once you increase the molecular weight and once you increase the branching. So if you extend the series even further, more branching, higher molecular weight, you end up with so-called microgels. So these are particles in the size range of nanometers to micrometers, which are often swollen by the solvent. So if you want to know more about microgels, you can refer to this review. And I give just one example here where we used one peculiar microgel, which is permanently charged, positively charged. Now we can do the same game as before. We know that these microgels don't deposit at the electrode, but what we can do, we can adjust the equilibrium potential, we can oxidize, so these ferrocyanide will connect these chains, the whole polymer will collapse, the microgel will collapse, so small size, or we can extend the microgels once we reduce it. So this can be done in a reversible way, and we don't see any signs of absorption of these microgels on the platinum electrodes. Now, I want to turn to the last few slides regarding the micelles, the non-equilibrium micelles. So we developed together with Nick Warren, we developed a strategy to program the non-equilibrium state right away during the polymerization, right away during the preparation of the polymers. And this is done by so-called polymerization-induced self-assembly using a certain technique, raft polymerization. And the essence is that you have soluble polymer chains, so this dimethyl acrylamide, it's soluble in water, and you do the polymerization in water with two monomers which turn into a polymer which is not soluble at the conditions used. So that preparation conditions, and even at room temperature, it's not soluble, it's insoluble. So you extend this chain, and at a certain time, this insoluble chain will gather together into these small micelles. Now you extend the chain, these blue chains need more and more space, they cannot accommodate in this spherical domain anymore, and then you get worm-like micelles. And then even further, you get these vesicles. Hopefully you can see this is a hollowish structure. So that's well predicted by theory. That's what you typically get. But however, if you do the whole polymerization at low concentration of monomers and materials, then we see that we don't get this development, we get just only these spheres, And one reason for that is that at low synthesis concentration, there is a low amount of monomer, low amount of plasticizers, so there is hardly any mobility in this interior domains, meaning that there is no change for structural rearrangements, meaning you're trapped in this morphology here. Now, here, degree of polymerization of the insoluble block, synthesis concentration. At low synthesis concentration, we get only these spherical micelles. At high synthesis concentration, we get spherical micelles, worms, and vesicles. Now, we can take these vesicles diluted to the low synthesis concentration, meaning that we have the same polymer now, under the same conditions, but we have two different structures, two different micellar structures. And now we can play around with temperature. As I said, we can temperature is a means to make this blue block soluble. At low temperature, at around 8 degrees, it starts to become soluble. Now, we did a lot of small angle neutron scattering. We get from this curve structural parameters of our system, so we can extract here the core radius, the length of the crafts, and so on. So here we start at 25 degrees, we cool down, nothing happens, we cool down further at 5 degrees, the whole system disassembles into unimolecular dissolved chains. Now you heat up, then you get small micelles, you heat up further, you get now worm-like micelles which are entangled and interconnected. So at the same conditions, you turn low viscosity dispersion into a gel. The same conditions, but total different properties. And you can even follow that by rheology, that you have changes in the mechanical properties, and this gives a porous structure here in these gels. And this is seen not only by cryo-SEM, but also by super-resolution fluorescence microscopy. Now, this is done here for the preparation at low synthesis concentration. Now we take the same polymer, which is prepared at high synthesis concentration, but diluted back to low synthesis concentration. So we have these vesicles. We start again, we cool down, nothing happens. We dissolve it at 5 degrees. So then it's basically the same what we had before. We have the same steps. We get these small micelles, and we get these worms in the end. So we get the same procedure, but we start from a completely different structure in the very beginning. And even the mechanical response is basically the same as before because it's the same polymer, but we started from a very different structure. So it's a very peculiar system where we have all of the 3 different structures, spheres, vesicles, worms, for the same polymer, and you can adjust it by preparation and by using a trigger. Now, if you don't like this thermo switch, you can also use hydrostatic pressure, because this blue polymer, this made of poly and isopropyl acrylamide and polyterpyl acrylamide, is also pressure sensitive. So this may be interesting also for the oil business, where you apply pressure and then the material liquefies, but if you release the pressure, it becomes jelly. So here's an example. This is at room or ambient pressure, and then you apply hydrostatic pressure, 1,000 bars. The material will disassemble in unimolecular dissolved chains. Then you release the pressure, you get these micelles, and under certain conditions you even get these gels. So you get also back these jelly materials, these worm-like micelles. So I hope I could show you that non-equilibrium allows electrochemical manipulation to achieve E-micellization or E-microgels. And then I hope I could also show you that non-equilibrium state of micelles is beneficial because you can keep a certain system for years even. It doesn't change, but once you apply a trigger, it will run towards the equilibrium state, and major property changes are accompanied by that. So I want to thank my co-workers, my collaborators, the research funding, and I thank again you for listening and also for being here. I thank the organizers once more again. Thank you very much.
And now, Mr. Elvin Rustamli. He will be presenting his topic.
Thank you very much. So, welcome you all. I am Elvin Rustamli. Let me introduce myself firstly, then I will talk about my topic. The title is Conductive Polymers, a New Era in Technology. So, I am Elvin Rustamli, as I said. I am working as a chemist at Intertech company. in oil and gas industry and the executive director of Azerbaijan Chemical Society. And I am also PhD at Baku State University. My research area is conductive polymer. Here's my outline. I will give you a brief introduction about conductive polymers, their properties and applications. Then you will see the construction and characterization of electrochromic device. The organic polymers with conduct electricity are known as conductive polymers. About 40 years ago, all the carbon-based polymers were thought to be insulators, but in 1977, it was found by Doug Shirakawa, Alan McDermott, and Alan Higger that films of polyethylene increase their conductivity when they are exposed to iodine vapor. In 2000, these three scientists received the Nobel Prize in Chemistry for the discovery and development of conductive polymers. As I said, in 1977, conduction of polyethylene in acid by doping iodine, the halogen doping transforms polyethylene to a good conductor like a metal. Oxidation with iodine causes to be jerked out of the electrons of the conjugated polymer and leaving holes in the form of positive charge. As you see here, this positive charge can move along the chain. Removing electrons from conjugated polymer or inserting electrons into the conjugated polymer, this process is called doping process, and this material used in this process is called dopant. There are two types of doping process, oxidation with halogen or p-doping, and reduction with alkali metal. This is also called N-doping. The typical properties of conductive polymers are conductivity, flexibility, elasticity, stability, strength, ease of handling, and in addition to these properties, they are cheap compared with other material for using in some applications. Due to these attractive properties, conductive polymers can be used in specific applications such as organic solar cells, organic light emitting diodes, biosensors, and electrochromic devices or smart windows. Let's look some of these applications. First, organic solar cell. A solar cell is a device that converts the energy of sunlight into the electricity in a response to electric current by the photovoltaic effect. Here is the structure of organic solar cell. Glass substrate, indium tin oxide anode, active layer. Active layer is the conductive polymer. Here is the P.PSS bulk heterojunction. Lithium fluoride, and the cathode usually used aluminum, calcium, or magnesium. Let's look at the working principle of the organic solar cell. When the sunlight comes into the surface of organic solar cell, past the glass substrate and indium tin oxide anode, and arrive to active layer. Photons create holes and electrons in active layer. Then the holes go to the anode and the electrons go to the cathode, produce current and voltage. Another interesting application of conductive polymers is the organic light emitting diode. An OLED is one of the type of light emitting diode in which the emissive electroluminescent layer is organic compound. This organic compound emits light in a response to electric current. The first picture is the structure of OLED glass substrate. This also may be flexible, plastic or other. Indium tin oxide anode, conductive layer, emissive layer, and the cathode usually aluminum, calcium, or magnesium. Both of these layers are small molecules, maybe small molecules, or the conductive polymers. And the second picture is the working principle of organic light emitting diode. Let's look at how OLED creating light. When the voltage applied to electrochromic OLED, the cathode give electrons to the emissive layer, and the anode remove electrons from conductive layer. This also means that anode give holes to conductive layer. Holes are the positive charge. Then, due to electrostatic attract, holes jump to emissive layer and combine with electrons. After they combine, they release the extra energy as a form of light. Here you can see the different flexible OLED displays. OLEDs are used to create digital displays such as TV screens, computer monitors, and portable devices such as mobile phones, and digital newspapers, and other type of TV screens. We polymerize the conducting polymers according to donor acceptor theory, because minimizing the band gap is the important goal for the maximizing of conductivity. According to donor acceptor theory, if the both of donor and acceptor group will be in a conjugated polymer, we can obtain optimum small band gap. Band gap is the distance between the valence band and the conduction band. Here's the synthetic route for the monomers which I have synthesized. First one is the typhene containing, and another one is the thionyl containing. Then heterochemical polymerization of these monomers achieved, and the cycle voltmeter styles were explored. Cycle voltmetry is a convenient way of analyzing electroactivity of monomers and obtaining of oxidation and reduction peak potentials of polymers. For the first monomer, oxidation potential was observed at 0.95 volt, and for the second monomer, oxidation potential was observed at 1 volt. Spectral electrochemistry is the combination of electrochemical and spectroscope methods. Here we use the 3-electrode electrochemical cell, indium tin oxide anode as a working electrode, platinum as counter-electrode, and argentium as a reference electrode. Spectral chains were explored by using UV visible near-infrared spectrophotometer, and maximum absorptions were recorded for the both of polymers. For the first polymers, maximum absorption was observed at different nanometer, and the band gap calculated from the onset of this transition. For the first polymer, the band gap was 2 electron volt, and for the second polymer, the band gap calculated 1.7 electron volt. Electrochromism is the one of the type of chromism. This is reversible and visible change in color upon applied potential, and this potential leads oxidation and reduction. Color change between transparent state and the colored state, or between two colored states. Also, organic material may exhibit several colors. This is termed as multichromic, and this process is called multicolor electrochromism. Here you can see the different conductive polymers color change in intermediate, neutral, and n-doped or p-doped states. And here you can see the color change of my polymers. As you see, both of my polymers were multichromic, and it changed colors from yellow to blue, but second polymer exhibited in intermediate state green color too. And the kinetic studies of both of polymers were conducted in order to determine switching times and the percent transmittance change of polymers. Switching time is the time required for switching two extreme states of polymers. For the first polymer, switching time is 1 second at 490 nanometer, and for the second polymer, minimum switching time is the 0.2 second at 608 nanometer. And we construct electrochromic device using my second polymer and the common conjugated polymer P-dot, polyethylene dioxide thiophan. P-dot is anode color coloring, and my second polymer is cathode color coloring. These polymers are coated onto the transparent indium tin oxide electrodes, and the gel electrolyte was spread onto the polymer coated sides of electrodes. Then these electrodes sandwich under the atmospheric conditions. After the assembling device, cathode color coloring P-dot is fully oxidized, and my second polymer is fully reduced. And the color change of my electrochromic device from yellow to blue, when the negative potential applied to electrochromic device, and due to maximum absorption of my second polymer revealed the yellow color. And in that state, P dot layer was in transparent blue. And that's why electrochromic device revealed the yellow color. But when the applied potential increased, due to oxidation of P dot layer, the blue color became dominant. And the electrochromic device also revealed the yellow color, a blue color. The kinetic studies of electrochromic device also were conducted and determined the switching times and percent transmitter change of this device. Minimum switching time for the electrochromic device was 0.3 seconds. And also optical memory of electrochromic device was explored, and the optical memory is the ability of material to retain its absorption state after the electric field is removed. We paused 1 second to this device and then holding at open circuit conditions for 200 seconds and was evaluated optical memory. And also stability of electrochromic device was evaluated by continuous sweeping up to 500 cycles. You can see my electrochromic device was very stable up to 250 cycles. Here you can see the different types of smart windows. Smart windows, you can control the passing of sunlight into your home or workplace. And also you can use the transparent smart windows as TV screens or other game consoles and other screens. Conclusion, both two monomers were synthesized according to donor-acceptor theory, and these monomers polymerized via electrochemical way, and then using one of them we used to construct a electrochromic device. Here are the references, and I would like to thank Professor Dr. Levent Topar and Siraj Hasanov and Yasemin Arslanov for everything helps me. And also I would like to thank Horizon Education Agency for especially Anwar Mehmedli and his team for organizing this amazing symposium. And thank you all for your attention.
Thank you very much. And now, Mr. Elvin Abbasoglu will be going to present his topic.
So my name is Elmir. I'll be talking about the separation optimization by chemical application in oil and gas production. I'm a production chemist working in oil and gas production operations in BP Azerbaijan. I complete my degree in chemistry right now. I'm completing my Master of Engineering in Chemical Engineering department. So just wondering how many of you are from chemistry or chemical engineering background? Just raise your hands. So, too many. So you may find it interesting, and I try to keep it as understandable to everyone else. I try to keep it very interesting to everyone. So the summary is that I will start with process overview of oil and gas production, how we produce, and general overview, and then I will move to chemical aspects of produced fluids, how chemistry is related to this production, and then I will move to chemicals we use to optimize separation operations which are done in oil and gas. And these chemicals are demulsifiers, mainly antifoams that we use, and then I will talk about water clarifiers, and I will then move to performance monitoring, how we monitor the performance of these applications, and at the end I'll move to question and answers. But if you have any question, you can stop me anywhere and just ask your question. First of all, this is the This is the general overview of production process, basically offshore platform and where we produce oil and gas. So fluids coming from the wells, production reservoirs, through the production manifolds to multi-stage separation system, we usually have multi-stage separators. The first one is usually a high pressure separator. The second one is usually the low pressure separator, and where we have gas, water, and oil separated from each other. Depending on the process parameters, we may have some heat exchangers somewhere in the system. And we also have test manifolds, test separator. We use this part of the process to test the fluids, their new wells or some new applications to understand their future behavior. So this is mainly it. And in the next slide, I summarize the chemical injections, how we do the chemical applications in this system. Okay. So mainly the chemicals we use to optimize the separations are mainly demulsifiers, antifoams, and water clarifiers. So demulsifiers are mainly injected to the separator inlet. Antifoams are also injected where we expect a foaming. Before that location, we need to have some antifoam in place to avoid foaming issues in the system. And we also have water clarifier to purify the water coming out of the separator to the oil, to separate all the oil from that water. So this is the purpose of why water clarifiers are applied offshore. So mainly this system placed in an offshore platform. So the purpose of this system is to separate oil from gas and water to send oil as much clean as we can to the terminal, which is located on different areas. So the purpose is to have around 5% of water in the oil product, which can be as high as 80% from here, and 5% is the target of the oil product that we produce. So first of all, demulsifiers. They are also called emulsion breakers. So emulsions are the undissolved particles that's dissolved into immiscible solutions. So we use this kind of chemicals to demulsify the system. So these applications help us maintain 5 butter or even lower water content in the system. And they're usually injected upstream of the separation vessel. Where we have separation vessels, before that vessel, we need to inject this chemical to get efficiency of it as much as we can. And imagine this is a separation vessel. So I summarized the emulsification in 4 steps. First of all, these are little droplets of water in the system. And these are total oil. So we need this water all completely separated from the system because it doesn't make any money. So we need oil because it brings us energy. We use it for different applications, but water needs to be separated from this system. So first of all, we have water droplets in this system. Imagine this is a separator. And when we apply this demulsifier or emulsion breaker to the system, these molecules come and find these water droplets, and because they are surface active chemicals, they change the surface activity of these water molecules, and they become more attractive to each other, and in the third part, they coalesce. So they get closer to each other. When they are big enough to settle out, they just settle down here, which is easier to separate, to get the water out. We need long enough contact time of the chemical to system to have this efficient separation. And this settlement of these water molecules can be explained by Stokes' law settlement, so which says that the velocity of the droplet down the system depends on the droplet size, the density difference of the droplet and of the system fluid, gravitational force, and viscosity. Which means also if we increase the heat, so it will reduce the viscosity and we will get good separation. And also if the droplet size are bigger, it's easier to separate because it's in this part, and these are directly proportional to this. So these demulsifiers help us to increase this velocity of the droplets to get them down and separate them from the system. So emulsion breakers or demulsifiers, they're mostly non-ionic polymer chemicals, but we may also have some kind of charged chemicals, polymeric, anionic or cationic. Their molecular weights are about 2,000 and 50,000, and their injection rates up to 30 ppm. This is the injection rate we usually apply. So for example, if the production rate of oil is 100,000 barrels a day, we need to inject 20 liters an hour of this chemical to treat the system and to get good separation efficiency. They can be injected anywhere downhole in the reservoir or in the wellheads where the reservoir fluids come up the surface or on the separators. And some demulsifiers are better than others. So you may always find a better product than your product, than the one you're currently using. So you need continuous improvement of your chemistry and of your system to see how you can optimize your separation. And it's also important to note that all emulsions can be treated. So some emulsions are very hard to treat. Some waters cannot be separated at all. But a good demulsifier can help us do that. So some product examples. The most commonly used application of demulsifier, this is the chemistry, alkyl phenol aldehyde ricin alkoxylate. So it's basically the alkyl phenol aldehyde. Alkyl phenols are condensed with aldehyde and then ethoxylated with ethylene oxide and propylene oxide to get this product. And this is another type of polymer that can be used as demulsifier. It's formed from 2,6-toluene diisocyanate, and it's a polyethylene polyoxalate. So these two chemicals can be used together. So in some part of the world, they use this chemical together, and they get better separation efficiency. And some people try to use only one. Some people try to get different formulations depending on their process and depending on their chemistry of the fluids. So I try to show how the demulsifiers behave in the system. So this is actually a three-phase horizontal separator where we have oil, water, and gas coming into the separator here. We have three-phase here, and sands or solids are going down right here, and we have water and oil here. Above this weir, the oil flows to the oil outlet where we need to have 5% or less water content. And gas are moving up to the system where we extract or get the water from this lake. So this is I put actually a video. I'm trying to open it. I just tried to show how demulsifier work in the system. They separate oil from water. But okay, so what we need is to have this is real oil sample from the well or from the separator with emulsified water. When we apply the emulsifier, they get separated. And this is what we need to happen right here to get better oil product. So this is all about the emulsifiers. And so the emulsifier applied to this bottle, which is mainly composed of oil and water. Now, and after some time, so you can see the difference. I'll move to the antifoams, so the video didn't work well. So antifoams are kind of chemicals that we use to optimize the separation efficiency in the system. So this is what foam is, actually. When you pour acidified pressurized fluid or drink to the glass, and if you are not very careful, you may get this. This is something we don't want to have in our process, because in three-phase separator, the foam can cause too many problems. First of all, I need to note that the poor liquids do not foam. If you have only water, it doesn't foam. You need to have some surface active components in that to have foaming, and it's caused by surface activity, and no foam is stable forever. No matter how foamy your liquid is, if you leave it for few hours, it will go, the foam will collapse. But unfortunately, we don't have that long duration in our system. We only have a few seconds to collapse this foam, which is why we need antifoams, antifoam chemical. So what's wrong with foam is that they, as I said, the poor level control in the vessel is the first foaming concern in the system. And also when there's a foaming, we may have some carryover of liquid to the gas outlet of the separators, which may have downstream problems. And compressor trips are one of them, which needs to be avoided. And gas also carry over to this oil outlet where it shouldn't, where we shouldn't have gas in the oil outlet. We should separate water, oil, and gas separately as much as we can.
Eldar Mansimov, Caspian Drilling Company, co-work operation, well drilling operator. Just you said, thank you first of all for great presentation, Mr. Elmir. My question is you just spoke about the advantages of this presentation of the default.
Antifoams.
Yes. And what's the disadvantages of? Because being a disadvantage, as I know, it's sensitive to the minerals, and also it should change at the pH changes. And how you control such kind of situations?
Yeah, the good question actually. But when you introduce a new chemical to the system, so you have to be aware of the risks you are bringing to the system. You have to be aware of its chemical behavior in the system and its compatibility with system fluids, with the system material, and the other chemicals you are injecting, and even the downstream process facilities. For example, if I'm using a chemical in an offshore platform, I may have some problems happening in somewhere in a different country where they use that crude oil for producing different products. So that's why when you introduce new chemical, you already have your information, what you should expect, and you have to decide, do you take that risk or that risk? So you have to understand the difference of that risk. You have to accept one of them. If the second risk is not acceptable, you just don't introduce and stay. Yes. Whichever benefits you more, you can take that one as an advantage and take the risk of the other. Did I answer your question?
Yeah, of course, thank you.
So yeah, antifoams or defoamers, how they work. So imagine this is a crude oil film between two gas bubbles. So these are gas bubbles and these are crude oil. And when I inject antifoam to this system, it spreads at the interface and breaks the film of oil so that we do not have any oil going up, any foaming issue. So this is basically the general principle of antifoams and how they work. And their application is basically done upstream of the foaming concerns, where you expect your foaming to happen. In the separator, so you have to inject before the separator. If that happens in some kind of flash tank, you have to be injecting your chemical upstream before your fluid goes to the flash tank. That's the injection location of the antifoams. And typical injection rates are 1 to 15 ppm. You may have efficiency at 1 ppm, or even you may have to increase your dose rate to 15 or 10 to get good foam collapse. But increasing the chemical rate is not always a solution. So when you overdose your chemical, you have to be very careful because it may have some reverse effects. You may have some, while you're solving a problem, you may have your worst problems in the system. That's why you have to be very careful in measuring the chemical injection rates in your system. And commonly used antifoams are silicones usually. This is one example, it's a PDMS, polydimethyl siloxane. And glycol-based antifoams are also used in glycol system. We can also use this in crude oil system by formulating some kind of polar solvent, non-polar solvents. So lastly, water clarifiers. So when we separate water, unfortunately it's not 100% water. We have some residual oil in that. So while I was talking about water and oil emulsion, So this is oil and blue droplets are water. The reverse emulsion is that when you have water, the main phase, and oil droplets here. So this is a concern. This is a water quality issue because it's a serious environmental concern for offshore operations. If you produce water from the system and you separate that water, you use an offshore platform, you have to keep it as clean as possible because it contains oil if it's discharged to the sea or any marine environment. So you contaminate that system. That's why you have to be able to clean your water as much as you can. And target is usually below 30 milligram per liter. For each liter of produced water, you have to have less than 30 milligrams of oil. So this is very strict target, and it's a very big challenge to reach this target, to keep your oil concentration below this. And this oil droplets also damage the process equipment. So you don't want this because it may plug your pumps, filters, or injection equipment. And I put a typical offshore produced water system in North Sea. While we have water separation in this part of the systems, this is a multi-stage separation system where we have water separated here and oil separated here, which is sent for further treatment. But waters from each separator are separated and treated by mechanical treatment units, which are usually hydrocyclone, flotation vessel, or degasser. We need some kind of chemical to help these mechanical units separate oil better. So this chemical are called water clarifier. They clarify water. This is the general name. It has some kind of different chemistries, up to hundreds or thousands. So how they work? So first of all, this is the dispersion of oil droplets. So it's like dishwasher in your kitchen. So if you have pour some kind of oil to your water, and you have this picture, unfortunately. And some of these oil droplets are charged, plus or minus. When you apply water clarifier to this solution, they unbalance their charge. For example, plus charges become 0, and negative charges on the droplets, they become 0 again, and so they become more attractive to each other, and they start coagulating. They get together and get bigger and bigger, and this is the oil coagulated by the droplets here with the help of the chemical we apply. And at the end, they separate, the oil forms a separate layer and goes up because of density. So typical dosage is 5 to 20 ppm, parts per million. And there are two types of water clarifiers. General classes are flocculants and coagulants. The flocculants are usually polymers, and they induce the settling particles and grow into larger flakes like this. So this is actually a physical process. So the type of chemical, I just put an example here. This is a DADM AC polymer. We actually don't care about the chemical formulation, the chemical composition of this flocculant, because it's a physical process. You only need to coagulate floc to make bigger floc to make your separation efficient. So that's why if the polymer is okay, you have to apply that chemical, that system, and get your separation along with the coagulants. Coagulants are water-soluble water clarifiers, and what their function is, what they do is they, as I told in the second step, they imbalance the charges of oil droplets so that they become attractive to each other. So they get close to each other, and while they were minus and plus, they are not attractive. They do not attract, they repel each other, but when they are recharged, they are becoming neutralized and start liking each other. So they get together. So this is the function of the coagulant, how they work. About these three chemicals, the three types of chemicals, and how we monitor their performance. How do we know that these chemicals work? So basically, for each chemical application, we need to have monitoring parameter and usual target for it. I'm injecting this chemical. So why am I injecting this chemical? Because I need to lower my water content in the oil product. I need to have at least 5% of water in oil. That's why I need to monitor the water content of crude oil product. I take sample, go to the field, take samples, and look for the water composition, water content, and I say it's 3%, okay, that's fine, so we are good. So usual target is -5, less than 5, sorry. So the chemical application, the number 2, antifoam, and monitoring parameter is liquid carryover to the gas outlet. We keep records of the gas analysis that we also look for the liquids in that gas, so make sure that we are not foaming in the system. And it needs to be below the process specific limit, which is defined by the project team when they design the system. And it also affect the, as I said in the previous slide, the level control. That's why we need to monitor the level control. We need to be very careful when we control the level because we don't want any high alarm due to foaming. So you have to be very sure that you are not foaming the system and your chemical application is in place and you keep dosing your chemical to avoid foaming in the separator. And water clarifiers are monitored, their performance are monitored by oil concentration in the produced water. We analyze water samples for oil concentration and we try to stay below 30 milligram per liter. If we are above this target, we have to do something. We have to think something differently to keep our concentration below 30 milligram per liter. So all in all, the summary is good oil, water, gas separation requires good chemical treatments. If your chemical treatments are good, so you will get your separation efficient as long as your mechanical separation is also working well. But overdosing is not always a solution. While you try to solve a problem, make sure that you are not creating something worse. You are not causing something worse. That's why you have to be aware of all the risks that our friend just asked a question about. And you also have to monitor your system continuously to make sure that you are treating the system as you should. And last thing, I would say that there's always a better product and an opportunity for optimization. If your demulsifier or water clarifier or antifoam are working well, so it doesn't mean it's the best product. You can always find a different product which can work at different dose rates, lower dose rates, or you can optimize your current chemical treatment. If you're, for example, injecting 20 liters a day, why not to inject 10 liters a day? Did you check it? So you can just optimize your system by playing on the chemical injection rates and doing analysis from the system and get your most efficient process conditions and keep operating as safe as you can. That was all actually. I hope you enjoyed it. Any questions?
Hi, I'm Akbar Jallo. Thanks for giving a lot of information about this valuable topic. I have a question about the first stage separation process. Can we separate gas from oil, water, I don't know, sand mixing by some chemical? For example, monoethylene glycol and other chemical.
You can, first of all, the separation by chemicals are done when there's the concentrations are very low. For example, you can, if you try to get 0.1% of some contamination you have, you can use chemical. But generally, what we use for separation is for mechanical units like separators or flush tanks or distillation towers or cooling towers. Chemical treatments are secondary barriers that we apply to improve these mechanical treatment units, actually. But purely just applying the chemical to the system, it would be very expensive because you can do it by mechanical operations. Why to invest too much on your chemical application? So chemicals are helping that mechanical because mechanical separation units are cost efficient, but when at some degree it's not 100% efficient, so it needs some help from the chemicals. That's what we do, actually.
Thanks.
Did I answer your question?
Hello, hi. Can I ask you a question, by the way?
Yes.
Actually, it's a very great presentation. We know that the emulsifier is a very good solution, by the way. I mean, that's why it has been used by industry for years and years. But my question, or maybe just to get you some opinion, if we put something like chemical, the emulsifier, will that be affecting the quality of the crude itself?
Emulsifiers?
Yes, and my second question will be then, crude and water, in order for them to be emulsified, they need energy. This energy comes from the flow. Can we, for example, design a system in the production, maybe in terms of the pipeline and so on, that we can actually reduce this energy so that there's a less emulsion problem, rather than treating with some chemical?
Yeah. The answer to your first question, using emulsifier, not demulsifier, is actually a practice done in oil and gas operations. It's when the wells are not flowing well, for example, if the pressure is very low, bottom hole or down hole, we introduce some kind of emulsifying chemicals. It brings some foam. It energizes the system to keep the well flowing. So this is where we apply emulsifier. But when it comes to the surface, so it needs to be demulsified because we need to separate the water from it. That's where we apply demulsifier. So this is the answer to your first question. So emulsifiers are applied, actually. The second question is, yes, we need to reduce the energy of the system. That's why in the presentation, if you remember, I put multi-stage separation. The first one is high pressure. The second one is low pressure. And to get a good separation at the end, your end point have to be atmospheric or even below atmospheric pressure. So we usually have HPLP separators on the offshore platform, which operates at 10, 15, or 20 bar, and it's pumped through the subsea pipeline to the terminals where we have atmospheric separation. At the end, we neutralize the energy we are having from the wells just to have good separation, and at the outlet of the oil and gas terminal, which is located on shore, is 0.3 or 0.2% of water. So yes, we reduce the energy and we get good separation by doing so. Good. Thank you.
The Association of Azerbaijani Academics in Germany. This association is a democratic, independent, educational and cultural organization of Azerbaijani students and scholars in Germany. It is founded in 2007. The association concentrates on the following areas. First, to contribute to the integration of Azerbaijani students and scholars into German society, cooperation with other democratic organizations of similar profile, exchange and discussion of the Azerbaijani living in Germany with German culture and society, presentation of Azerbaijani culture in Germany for better international understanding, contribution of knowledge transfer between German and Azerbaijani universities, linking new contacts between universities and two countries. The association regularly organizes at least one scientific conference at a German university in a year. In addition, it organizes annual and some other meetings on cultural and social level. There are some projects of association too. One of them is scholarship program named after Mehmed Emin Rasulzadeh. the founder of the first democratic republic of Azerbaijan. Other project is translation of a medical book from German into Azerbaijani. In order to carry out these projects, still each one needs donation. At the moment, our first panel, namely geoscience, is beginning. I want to invite here Professor George Barakos. He's from Greece, and at the present time, he does postdoc at a German university. Our second speaker of third panel, Dr. Elshan Abdullayev. He is lecturer at the Azerbaijani University now. And you know him, Enver Mehmedli.
Okay, good evening, everyone. First of all, I would like to thank everyone, Anvar and his team, for having me here. It's a great opportunity, a great country, a great city, and up to now, it's a very, very nice and interesting symposium. So, when I was asked to give a talk, I asked Anvar, what should I talk about? And he said, mining engineering in general and education. I said, how many hours do you want me to talk? He said 20 minutes. I said, okay. So today I'm going to just scratch the surface about mining engineering. It's not going to be a technical presentation like you saw the previous ones. It's a more general one, but I hope that you like it and you find it interesting. So it's the view of an engineer, my view of how the mining life cycle is going on. But first, to catch up with the previous talkers and the next ones, we're here about engineering. What is an engineer? Don't expect an engineer to write poems or paint paintings or everything. What we do as engineers, we take natural science, we take mathematic facts, and we develop things, buildings, constructions for our everyday life. So we're good at math. And here you can see some of the engineering miracles. Aeroplanes, big ships, Burj Khalifa, everything. Robotics, science. My colleagues from the mechanical engineering discipline will talk about them later, and from EIT, so to connect with all the disciplines together. But then, what comes to your mind, and that's a question now, when you hear the word mining engineer? Please, anyone? Yes. Geology. Geophysics. As a profession, I'm a mining engineer. You see me in a costume. That's rare. That's only for conferences. Normally, when you hear the word mining engineer, you expect to see people like that. Not yet ready for dinner. Or this gentleman over here just came out of the office. Well, that could be, these are miners, but these were used to be miners of an old era. My impression, and what should be your impression about mining engineers today, should be something like that. And this photo is taken from the research and educational mine that we have in Freiberg as our laboratory in Germany. And these are my colleagues, PhD students. And what you see, they're trying to catch up with new technologies using robots. So all disciplines are together. They are joined together in mining. And of course, we do our own engineering miracles. We can mine everywhere, from the middle of Siberia with snow to northern Canada between lakes, up to a depth of about 4 kilometers down nowadays in South Africa. And of course, we are using big toys, like big trucks here, you can see. Now, why mining is important, and for me, I'll have to share a secret with you here now. Mining is a mother of all engineering disciplines. So, if it were not for mining engineers, all the other engineers would not have material to work on. And why I'm saying that? Civil engineers construct roads, bridges, houses, buildings, but they need material. Steel, stone, cement. If a mining engineer doesn't mind that, they don't have the material to work on. The same for chemical engineers or for EIT engineers about gadgets, smartphones, or in agriculture or in energy, in oil engineering as well. Even your clothes, everything has minerals or metals. You've heard about metallic water. In fact, Anvar, can you give me some of the metals that you have on you?
Something from the Freiberg.
Let me help you. Can you give me some of your metals?
And my phone, of course.
Of course. So this here, you may not see it, but without precious metals, gold, silver, rare earth elements, it cannot work. You need it for the screen, you need it for the hearing, you need it for the display, for everything. And not only smartphones. Another example, batteries. Batteries for the vehicles. And you see here, they need lithium, they need nickel, cadmium. All these are metals and minerals that have to be mined from the surface or underground. But here comes another secret, that, of course, mining is the mother of all engineering, but this is what miners get. And we cannot put just the raw material inside the batteries or inside the phones. There has to be a process. And here, for example, we need chemical engineers, and what they were talking about before. We need mechanical engineers. We need a collaboration of all these disciplines in order to have the purified metals with the specific properties that at the end will give us what we want. And here another very simplified diagram. So, turning from ragstone through cracking, through metallurgy, separation, refining, to all these products that we use nowadays. And that brings us now to the life cycle of a mine. How do we find them? Do we just dig in luck without knowing? Do we mine it and just send it to the mill and then to the process? No, it's a whole procedure, a sophisticated procedure, starting with prospecting and exploration. That might take 2 to 8 years. So we need geologists, geophysicists, as you already mentioned, mining engineers, to find the properties, to find the deposit, to dig for it, to make drill holes, as I'll show you later. And this can take several years. And it can cost from 0.5 to even $15 million. What comes next? You find the deposit. You have to see how you plan it, how you develop it. You make mining method programs. You see what kind of equipment you're going to use. What are your costs going to be? This could take 4 to 12 years. And then the infrastructure, depending. I showed you a very big mine before. That big mine needs also very big infrastructure, meaning that it could go from 1 million to 1 billion. These are figures that may scare you now, but the profit out of these projects could be even bigger. And if there is no profit, of course, there would be no project. Then comes the actual mining, the extraction on the surface or underground as well. Could take from 5 to 100 years. In 2018, the coal mines in Germany were closed after 168 years of continuous active mining. We are talking about billions of tons of coal. And after that, we've got what is closure? You cannot just abandon the mine like that. I mean, in the surface, you have to fix the area again so that it looks nice. But also in an underground mine, you may flood it with water. You have to see and make sure that the metals, the toxics that you have used, that are released, they're not coming into contact with your groundwater, with the surrounding ecosystem. And that could take from 2 years to 50 years. Now, when it goes to exploration, again, new technology used. 50 years ago, they were using photographs from aeroplanes, or they were going on foot. Now they're using drones, much easier to scan the area. And after they scan the area, they go and drill. And they could drill for hundreds of meters down. And they could have a pattern of drills in order to see where is my deposit, at what depth, make metallurgical tests. Does it worth it? How big is it? What is the grade of distribution? And then they take these cores and they analyze them with a microscope, with tests, with everything. And then comes the modeling. So they take these cores, you see here, the drill cores all together, and they make the block models. This shows the ore and it shows where the precious minerals are. You can see it here as well from the surface. And you develop, you calculate your reserves, your resources, and then your reserves. And then you know, how can I mine it? You go and plan it. And its model, its cell here, has a specific value. Some of higher value, some of lower value. And then you go and say, how do I mine it? If it's very close to surface, probably I go dig around and have surface mining. All these that I'm showing you now are things that we are teaching or being taught in Freiburg, in the broader discipline of mining engineering and geosciences. What happens if my deposit is very deep? Then I go underground. I go with shafts. I go with drifts, with openings, development in order to approach the deposit and take the ore out, to extract it, to take it into surface and go on. And then I have to make my calculations. I'm an engineer, I need math. I cannot do without them. How many million tons can I produce per day? What is my cut-off grade? What are my capital costs? Are they 1 million? Are they 50 millions? Are they 1 billion? What are my operating costs every day? How many years the mine would exist? And so on. So many parameters, which if you put together, they all consist the mine planning. It's not just how deep the deposit is or what the shape of it is. It's also its geology. It's also its contact, rock mechanics. It's also its economic aspects, the costs, environmental aspects. Let's say that you find a very, very big gold deposit just beneath Baku. Would you mine it? Would be difficult, because then you have to relocate people out of Baku. Would you do it? Probably not. So, environmental aspects, socio-political aspects as well. Processing, market outlook. Is it a good metal, a good mineral? Can I sell it? Or I will just mine it and I cannot do anything yet, and then I have a stock of it and I'm broke. And after I plan, I go to the actual operations. And that is why for this symposium I chose not to have a technical, as much as possible, not a technical presentation, but just show figures. What do? Again, we drill, we put explosives, we blast the ore in a surface mine. Then we load it in these small trucks that you saw before in the picture. We go into the crusher and then to further processing. That's on surface mining. What happens when we're going to underground mining? Again, we drill horizontally or vertically or in any direction our mining method says that we have to do. Then we blast. Of course, it's very, very difficult and very dangerous to be close to a blast underground. That's why there are no pictures. But then you go and take the extracted ore and again, crush it, make it smaller particles, and process it. I won't lie to you, it's not easy. It is an exciting profession, but it's not easy. And it can be dangerous, both in surface, but also more particularly in underground mining. And that's why, for example, you have to take precaution measurements. Like, for example, having roofs while you're drilling, or putting support. Or, since you're in a place that has just been opened, you have to ventilate, you have to put fresh air inside. not just for people to breathe, but also for the toxic gases from the explosion to get out so that you can work again. And of course, you should monitor all the time. Nowadays, using tablets, using sensors, doing it automatically inside the mine. The whole process, actually, here you can see remote drilling. The whole process is going to automation, and that could be actually the future of mining engineering for those that could be interested in. And of course, it's not just mining itself. As I said, it's the infrastructure. You have to maintain these tracks. And what is if you're underground, 800, 1,000 meters down deep? You have to have a workshop there. You cannot afford to take the machines up to the surface, fix them, and put them again down. So what do? You have a whole workshop down there. The same for the facilities for the miners. Here you see this is a mine in Finland in 1,500 meters deep. And here you can see the cafeteria. It has internet access. I have checked it. Coffee and so on, because it's a hard profession. 8 hours. The miner has to get some rest. So it's not efficient for him to go up again and go down again. So there are facilities underground. And of course for safety as well. And what happens after mining? That's not my field, but I had to put it in. Processing, metallurgy, chemical engineering. And here you can see different ways from flotation, from solvent extraction, and so on, from different companies. Because you have to take this ore, you have to purify the metals and use the metals with their properties. And of course, environmental concerns, something that Anvar will talk later on about in more detail. But it's something that has to be important because this is a scene that you can see in China. And this as well. And we don't want to see this picture. Mining could be harmful for the environment, but actually not mining, but practices in mining. If mining follows the regulation and everything is according to the plan, then probably, hopefully, nothing will happen. But if you don't follow the rules, then you might get severe environmental pollution. And what do? Either in that case or when you're done with mining. You have the post-mining session. You have to rehabilitate your area. If you have a surface mine and nobody wants to see an abandoned surface mine living like a scars in the surface of the earth. So what do? You rehabilitate the area. And that is from Vismuth, that is close to Freiberg. It used to be uranium mining, surface and underground. And it was abandoned. And then a program was funded of about 8 billion euros in order to rehabilitate this in 15 years' time. Actually now, the area is also used as a park for families to go there. There's also a playground. There are athletic facilities and so on. And this may take for years. Here in Canada, after post-mining, they go even to the surrounding ecosystem to see if water has been contaminated and if that has gone to the aquifers, far away from the mine, or to the plants as well. And this procedure could take about 20, 30, 40 years, depending. If, for example, you have uranium mining, you have radiation, you have to be very, very careful about these issues in post-mining. To close this short presentation, I didn't want to put any comments or conclusions. I just wanted, out of curiosity for myself as well, to see the mining industry map in Azerbaijan. And you can see here that you had $20 billion from exports of fuels, of course, oil is number one, and other products. Mining and quarrying accounted for about 30% of the GDP in 2014. And you have 768 enterprises engaging in mine activities in general. What kind of mines? Let's start with the metals. you have alumina, you have copper, gold, iron, steel, silver. Let's go to the industrial minerals. Bentonite, soda, cement, gypsum, iodine, limestone, salt, sulfidic acid. Of course, when it comes to fuel energy, natural gas and petroleum. So it's a rich country, and it has mining potentials. Therefore, it should have potentials for its mining education. And with that, I'd like to thank you. I don't know if we have time for questions now or for later on. I'll be happy to answer.
So.
I gave you back your medals? Yes, I did.
Yeah. Okay. So thank you so much, Dr. Barakos. Dr. Barakos is also my supervisor.
You don't have to tell that. That's a secret.
Yeah. So already he just gave the speech about the mining industry and the mining engineering. However, today I will talk about some secrets of the mining and the other side of the mining, and I will try to tackle how we can tackle this problem. So the name of the topic is the create environmental balance after the mining. So we know that the mining is indivisible with environment. So actually when we see that, when you see it as the balance, you will see one of the hardest environment, and the other one is the money. So it means a mining, because for getting a money, we need some metals and minerals, and the government also support this kind of things, or businessmen. However, one thing they are just forgot. So the mining, one woman from India told these things: it is not investment if you are destroying the planet. So one woman, Vandana Shiva, she is environmental activist. Of course, this is really reality is like if we don't rehabilitate it, we already destroyed the environment. So, but this words has the opposite side as well. We can get what we want, because we also need to improve our society, and we, as Dr. Barakos has told, that every time we use that, even in phones or even this one microphone, that we use some metals. So therefore, we really need to crush the ores or the drill and just to get some minerals and metals. So, but you can see that before mining and after mining. So before mining, it was really good places. So after mining, but actually this is the ban of mining. So if that was like this, so the mining and environment. So mining inevitability disturbs the environments. It's true, because of in the United States, and you can see at the first. Here's the one person's just use 17 tons of the metals in 1 year, and you can see his whole life he used a lot of minerals. And for this one, the global extractions of the minerals and resources in 1980 till 2008, so the metals are more, they increased year by year. So, and I want to also to say that one of the bad things for our environment is the acid mine drainage. So it's also related with chemistry, and so you can see this is we also call that the yellow boys. So before the mining, you can see it was like the raining or the surface is relaxed, but after mining there is just so the procedures was like this: the oxygen plus water and the sulfate. So there is in the ores is the pyrites and the breakdown, and then the sulfuric the acids is coming, and the acid mine drainage just the influence to the animals. So in the oceans or just in the groundwater, so you can see it's going to the oceans or the lake or the sea. So here you can see the fish, because of the sodium, and the acidity is really high in an acid mine drainage. So another environmental damage of the mining, we cannot say that there is just some states. Actually, they were using the methods of the mining is like open pit mining, underground mining, in situ leach mining, and heap leaching mining. And there is also the it's a not soil the mining, it's the brine mining, but so open pit mining it's also there is a lot of the toxic and minerals surrounding the surface. And underground mining, there is a tunnel methods, so we are just using, and there is the high radioactive metals surrounding to the environment as well. And the in situ leaching, the mining, it's good for it's different than open pit mining and underground mining. However, there is in this one. There is acidity is really high, and it's also the influence to our environment. But here is the heap leaching, and it's in really dangerous methods in the minings as well. There is, and I remember, so in United States in 1989. During this period, approximately 7,000 animals that died because of cyanide, so the heap leaching. And additional environmental problems with the mining, erosion, water pollution, so it's the acidity as well, so, and deforestation. Because of the when they are just finding some minings, they are the drilling and methods, and as a result, so the impact of the environment, yeah, the results, it's not good because of the disability and the health problems in the mining, because of mining. But however, there is also the reclamation. Where is this? The reclamation is, so where reclamation takes place is here's everywhere where the land use has taken places. So you can see the surface of the exploration and the prospecting, surface mine, the dumps, the tailings, industrial plants of the mining and low soil, and collected area, the above underground mining. So that reclamation helped to make better our environment. And what is rehabilitation? It's almost the same, because we rehabilitate our environment. So here is, you see, before the minings and after mining, during mining as well. So the procedures was like this, and after rehabilitation, when the people just came to try to rehabilitate the minings, so you can see this kind of the pictures. As I remember, and when we were in Germany, so we visited to the Wismut, and probably you saw previous slides. So they was, after the Wismut, we went to one place. There was a lake, and another doctor told us, if you go to the lake, you will lose your hair because of the acidity is so high, and acid mine drainage. After the mining, they just make some a lake for for making a beautiful environment, but they need a lot of rehabilitation. So acid mine treatments, we cannot say that there is a lot of the treatments that actually is the waste. The acid mine drainage is also the big topic, but a little bit I will just say that. So there is a passive treatment, active treatment. So here's the passive treatments that we are using because of sulfate is going to the sulfate. So, and the aquifers, you know, that the mine tailings here and contaminated water, and so as a result, it's the remediated water. So it's helpful for our environment. And there is also another method is the active treatment, and also the some of the alkalinity we used for the procedures, and also the biological waste that's also in passive treatments. So the operations, so we use the for the pollution, environment, the landform, and negative seeds, and the microorganisms, flora and the fauna. That's all of them, and it's environmental impact assessment report. So, and I'm going to the last slides is preserving the environment. So here is the prediction, monitoring, the post-mining, monitoring, and evolving ecosystems. As a result, so with them, we can make the main message is here, we can get the money, of course, but there is a lot of abandoned mining in the countries, and we just damage to environment. However, we also need the money, but we should just make the balance. So we can get the money and we can rehabilitate the environment because of the we're living in this surface of the world. So, and that's all. Thank you so much for your attention.